All right, for chapter 10, let me dim the lights a little bit. For chapter 10, I'm going to ask you guys to do a little bit of studying at home. I want you to review sections 10.1 through 10.3 at home. And what I've done on the website is I've posted some links to videos in case you would rather watch the video than read your textbook. They're about 7 minutes long each. One section is on nomenclature. And the other is on acid-base reactions. With alkynes. So they're really short videos. I just want to try to focus our class time on going over mechanisms because those tend to be the most challenging aspects of Chapter 10. I don't want to waste too much time on review material. But let's start off by talking about preparation of alkynes. And for those of you who had me last term, we actually had a problem of the day where I introduced you to this in Chapter 8. But let's try to do a little bit of background before we dive too far into this. And most of these methods do go back to Chapter 8 reactions. Chapter 8, we talked a lot about elimination reactions. So let's say we've got this halide right here. And we react this with a strong base. What will happen? We'll form an alkene, right? So chapter 8, we saw that with an E2 reaction, you can grab a beta proton, kick off your leaving group. So we said this would be E2. And when we do this, we can form an alkene. We can do very, very similar reactions to form alkynes. But we just go one step further. So with alkynes, you can imagine having two halides. And I'll draw them both right here. And I'm going to draw in all of our hydrogens for right now on that terminal group. If we've got a strong base, we can grab an anticoplanar beta proton, clamp down, kick off our bromine, and when we do that, we form our alkene. It leaves one bromine behind. And then if we have a second equivalent of our base, we just do this one more time, and this was the problem of the day we saw last term, where we kick off our bromine that's remaining, and when we do this, we form phenylacetylene. These dihalides have a specific name. In this case, we've got two bromines coming off of the same carbon. What these are called are geminal dihalides. And Gemini in Latin means twins, so geminal dihalides mean both halides are coming off of that same carbon. Conversely, we can do it where these halides come off of different carbons. And if we have them coming off of different carbons, we call them vicinal dihalides. So I'm going to draw in all of our hydrogens. And again, the first step will be this E2 elimination reaction where we can clamp down, kick off our bromine. And when we do this, we're left with our bromine on one end And then our second equivalent, we've got our base that will come, grab our beta proton, clamp down, and again give us our phenylacetylene. Sorry, guys. Whoa. I'll slow down here. And these are called vicinal dihalides. So you can see in the top reaction, we did a double E2 reaction, and in the bottom reaction, we did a double E2 reaction. Yeah?
So these elimination reactions, is it a super strong base?
Yeah, you need to have it be a very strong base, something like sodium hydride, DBU, DBN. Any of those non-nucleophilic strong bases are preferred usually for these reactions. But typically any strong base will work well. The key for these preparation reactions is you typically see them and they go through a dual E2 reaction, and your beta proton still needs to be anticoplanar, just like we saw in chapter 8. The difference between these is one has both halides coming off of one carbon, the other one has them on adjacent carbons. Either of them work, though. So I've got a question for you guys. What happens if we have more base around? More than two equivalents of base? So let me change the color here. No, you're right. It keeps on going. The question is, where's our most acidic proton on that alkyne? It's going to be the sp hybridized proton, right? So if we've got a strong enough base and we've got a third equivalent around, this will come, grab that terminal proton. We stick with blue. And we form an acetylide ion. So oftentimes with these reactions, we have to be very careful with our equivalents of base that we're using. If we want to reprotonate this, oftentimes all we need to do is re-add water. And then this can reprotonate, grab its proton back from water, and then reform our acetylene. So why are acetylenes so acidic? Because of the hybridization, right? An sp hybridized bond is much, much more acidic than an sp3 hybridized bond. The pKa of an acetylene is typically about 25. The pKa of an sp3 hybridized bond is typically about 50. So we're talking about 25 orders of magnitude difference in acidity between an alkane and an alkyne. Yep?
So in the last step, do you also make hydroxide? And what does that just...
Yeah, so let's take a look at this. If we form OH minus, is OH minus a strong enough base? We know that the pKa of water is about 15. So in this case, water is more acidic than our alkyne, so it's going to push the reaction towards the product side. So in this case, hydroxide is not a strong enough base to deprotonate our alkyne. So again, this is where reviewing acidity on the supplemental lectures would come in handy, but we're not going to spend too much time covering this. This goes back to a lot of our chapter or our first term acid-base reactions. All right, so let's get a little bit into the reactions of alkynes. The good thing is chapter 9 already showed us a lot of these reactions in their most basic parts. So the first one will look very familiar to you. Let's talk about the reduction of alkynes. And so let's have a brief review. If we've got a double bond, an alkene, and we react it with hydrogen gas and palladium, what happens to that double bond?
It just goes away.
It goes away. It forms a single bond, right? So we go from an unsaturated system to a saturated system. That means it's saturated with hydrogen, right? If we think about alkynes, they behave in a very similar way. In particular, you can imagine, all right, let's say we've got this alkyne. Whoops, let me take this R off here. Theoretically, we could add one equivalent of hydrogen, react this with palladium. Then we would get our cis alkyne. And then if we add more hydrogen and palladium, we could go all the way to our alkane, right? The interesting thing about this is that we can't isolate our cis alkene. We only go straight to the alkane. So not able to isolate. When we do this reaction with alkynes, it's just like with alkenes. We go straight through all the way to the saturated alkane. So the real question is, how can we stop it at the alkene? If regular hydrogenation goes straight to the alkane, is there any way we can stop it at the alkene intermediate and isolate just the alkene? Because there are some situations where that becomes quite useful. So let's start a new section here. How can we stop at the alkene? And in order to do this, we have to use some special reagents. So if you saw up here, this intermediate, the cis alkene, was just simply too reactive. It went straight to the alkene. So we actually need a catalyst that is less active, something that raises up the activation energy a little bit higher. That way we can trap this intermediate that's really hard to isolate. And what we call this is a poisoned catalyst. We want a catalyst that's just simply not as good. Yep, they call it poisoned. And there's a few different catalysts that are used. The first one is called Lindlar's catalyst, Lindlar. And the actual catalyst that's used has a quinoline, which is this bicyclic ring system, along with lead and barium sulfate. And it's usually run in methanol. This is kind of a mess to write down on paper, so people normally just write Lindlar's catalyst and then assume you know that it involves this quinoline and this lead barium sulfate mixture. The other one that's often used is called the P2 catalyst. The P2 catalyst is another poison catalyst. In this case, it's a nickel-boron complex. So it's 2 nickels and 1 boron. Borons are a really interesting element because it behaves both with organic molecules and metals. So it oftentimes is a little promiscuous with how it behaves. So either of these systems work really well, and you can actually get your alkene out. So let's take an example of this. So I'm going to scroll up. I'll redraw these catalysts, so don't worry. Let's say we've got our alkyne. This time we're going to add hydrogen and Lindlar's catalyst. Are we going to get our cis alkene or our trans alkene? Cis alkene. So we talked about in chapter 9, that when we do hydrogenation, we add hydrogens syn to one another, right? So they're going to add to the same face. So if we look at this, we'll get a product where both of our hydrogens add on the same side. The same thing is observed if you use the P2 catalyst. So if we have this alkyne, and again we use hydrogen gas, but we use our nickel boron complex, we'll still get the same cis alkene. The key feature here is that both of these are trans to one another. Or sorry, cis, not trans. If we want to form the trans alkene, we actually have to use a completely different set of reagents, one where we're not doing a normal hydrogenation. And in order to do this, we actually have to use a metal, sodium. So if you look at sodium on the periodic table, it's all the way over in the left-hand column, right? Does that mean it wants to give or take an electron? It very much wants to give an electron, right? Sodium's more than happy being positive. So in this case, we're going to use sodium as an electron donor, and we're going to do hydrogenation, but we're going to do it in a radical mechanism. So let's take a look at trans alkenes. And this is called the dissolving metal reduction. So in this case, it's not a true hydrogenation. It's technically a radical reduction. So if we look at this, what we do is we can take our alkyne, we throw a sodium metal. So in order to specify that it's the metal, I normally put a 0 in the top corner. Your book sometimes does that, sometimes doesn't. And then they run this reaction in liquid ammonia that helps dissolve that metal. When you do this, you can actually get your trans alkene. The book introduces you to this mechanism a little bit. I'm going to skip that right now because we're going to talk about the mechanism for radical reactions in chapter 11. But for right now, just remember that the dissolving metal reduction gives you your trans alkene only. So it goes through a radical anion. We'll cover in chapter 11. It's a neat reaction. If you want to take a look at it in your book, you're more than welcome to. All right. Let's do a brief summary of these reactions because I know sometimes people get a little overwhelmed by these, but try not to get overwhelmed. They're fairly straightforward. If we have this regular alkyne and we want to go to the alkane, we said that we can use H2 and something like palladium, right? Just a simple reduction. We're adding hydrogen all the way across there. If we want to go to our cis alkene, we said that we need to use something like H2 and Lindlar's catalyst. What if we want to go from that alkene all the way to the alkane? What can we add to it? Just do a simple hydrogenation, right? So we saw this last chapter. We can do hydrogen palladium. If we want to get to our, trans alkene, we said that you can use sodium and ammonia. And then if we want to reduce that even further, we can. So now we've got the option to interconvert between an alkyne, an alkene, and an alkane, depending on which reagents we use. In this case, we need to pay attention to whether or not the alkene is cis or trans and choose the appropriate reagents to get there. If you want to reduce it down all the way to the alkane, you just use normal hydrogenation conditions. It's the cheapest and easiest. All right. Does that make sense? Yeah?
Just in case we have differences in traits, does it really matter if they're compound?
All that matters is, in this case, if you look at the hydrogen for the cis one, they always are installed on the same side. So you're always going to get your cis isomer out. If you do the dissolving medical reduction, they're always going to be trans. That's all I expect you to know as far as stereochemistry. So you can prefer the cis diastereomer over the trans one by selecting Lindlar's catalyst. All right, so let's start by going over to hydrohalogenation of alkynes. Again, this is really similar to last chapter. Oh. So hydrohalogenation of alkynes. Let's relate this back to what we just covered last week. We said if we had an alkene and HBr, will our bromine add Markovnikov or anti-Markovnikov? Markovnikov, right? So we said that the bromine will always add to the more substituted side of the alkene. If we do the same thing with an alkyne, we can come up with a hypothesis. We can say, all right, if we've got this alkyne, I keep on switching them, and hydrobromic acid, the first step should be that our alkyne pi bond will attack our proton, kick off our bromide. And when you do that, ideally what you should observe is a hydrogen adding to the less substituted side, and you form a carbocation. Then you'd say, well, now we've got bromide around. This bromide should be able to add back in to that cation. And we should be left with our mono-halo product, right? The problem is that the intermediate isn't correct. So this is called the vinylic carbocation. And it's not observed. So using this mechanism will get you to the right product, but it's not truly the right mechanism. The other interesting thing is if you experimentally run this reaction, you can derive a rate equation. And you can figure out that the rate equation is equal to your concentration of your alkyne times your concentration of HBr squared. So what's going on here? In order for the reaction to proceed, we need the alkyne to actually run into two equivalents of our HBr molecule, not just one. And so that experimental measurement forces us to come up with a new hypothesis. So our new hypothesis looks a little bit different, but gets us to the same product, and it's something we haven't really seen before. And this is common in organic chemistry, is you come up with data and then you have to modify your mechanism. So we're always looking for data that proves, or not proves, disproves a mechanism. If we have data that disproves a mechanism, we need to come up with a better mechanism that is more plausible. So in this new mechanism, what happens is we've got our alkyne, and I'm going to label this as CH3. I'm going to label this one as R. And we've got our acid down here, and we've got another equivalent of our acid up here. So what this is called is termolecular. We actually need 3 different reagents in order for this reaction to occur. These reactions are pretty rare. This sigma bond will go in, attack this carbon over there, and then the pi bond will go over, grab that proton, and kick it out. So let's draw the transition state. We're breaking this bond between the hydrogen and the halide. We're forming a new bond to this carbon. The hydrogen is still sticking out there. The CH3 is still attached. Part of that pi bond is breaking, and we're forming a new bond to this hydrogen, and then we're breaking a bond to that halide. So if we look at this, this is our transition state, and when we get to our final product, our halide adds from the bottom.
How about
Oops, sorry, this should be a H. Thank you. And we still get the product that we proposed in the last step. The difference is we go through a molecular transition state.
Why does the bond between H and X go to the triple bond versus the H going to the triple bond?
In this case, the triple bond's grabbing the proton on the top group. So if you look at it here, it's grabbing this one, and then our halogen's adding in. So if we look at the addition there, it's actually trans. So the halide is being added to the opposite side of the proton. The halide's coming from one equivalent of the acid, the proton's coming from another equivalent of the acid. So in this case, the product will be trans with respect to your halide and your proton. All right, for the problem of the day, it's asking you to look a little bit ahead in your book. You can hopefully try to work through this problem without looking ahead. But what this is called is a keto-enol tautomerization. And I wanted you guys to take a look at it before next class period because we're going to start using these equilibrium reactions a bit more. If you have any questions, though, feel free to email me or stop by my office.